All right, let's go for it here. This is 7.6. We're going to talk about something called polar coordinates. Now, probably something that you have not seen before in mathematics. We're going to look at polar coordinates. Eventually, we're going to look at ways we can graph things in polar, what we call graphing polar equations, technically here. That's what we want to do. All right, so let's go for it here. So what is a polar coordinate? So if you think about it on the X and Y grid, instead of graphing in terms of just an X and a Y variable, what this says, our value says how far do you go away from the origin, and then the theta value is your angle measurement, like we normally do in mathematics. So when you graph this, kind of looks like this here. Let me go back real quick here. So there it is. Think of this as, we call it the polar axis. So you can think of this as the X axis right here, and then you have the Y axis coming down. But really, in a sense, what you have is you have this whole concept of you got a length away from the origin as the first coordinate, and you got the angle measurement as the second coordinate. It's just a different way you can graph graphs. That's really it. In fact, in the face-to-face class, I always ask them, how many different ways do we have to graph graphs? How many different graphs are there? And the answer is somewhere between 11 and 13 graphs that we know how to graph, particularly two-dimensional graphs. It was pretty interesting stuff, but let's go for it. All right, so how do we do this here? So let's say we have a 3,60 degrees here, and so you can write them in terms of radian measurement. You can write it in terms of degrees. I think it'll be easier to sort of say degrees here. All right, and all these are going to represent really the same exact point. So if you say 3 units away, and notice I'm counting 3 units from the origin. So you have to almost like eyeball it a little bit, especially when you're going to be graphing them. You kind of say, okay, that's about 1 unit. So 1, 2, 3. So 60 degrees, think about where 60 degrees is, go out about 3 units, put a little dot there. There it is. Okay, what's another way? You can get the same exact dot if you go fully all the way around the unit circle, 1 full revolution, and then add 60. So 360 plus 60 more would give you 420. You're out 3 units, doing good there. You can also have negative degrees, absolutely. So negative degrees here, you can go negative 300. So that means you're going to go clockwise. And then again, 3 units out still gives you the same exact unit value here. There's one other type let's talk about in just a bit as well. All right, so practice problem number 1 for us. Here it is. Can you plot for me 2, negative 150? So let's do that for A. And if we go negative 150, and usually it's going to be past, let's see if we go, this is 0, this will be a negative 90, this will be negative 180, so 150 should be about right here. And then kind of mark off 2 units would be about 2 units here. I really don't have any units marked off for the X and Y coordinate. But if I would, then maybe like 1 would be about right here, 2 would be about right there. Anyways, the whole point is to have it right here. Okay, so that's A. And you would label it as 2, negative 150. All right, what we want to do is B. So B, we want to go, ooh, look at this. This is someone we did not see before yet here. Can we actually have R being a negative value? Absolutely. Negative value just means that you go the exact other way from the origin. So R less than 0, and we go from 0 to 360. So our degree value has to be a positive value, 1 full revolution at most, and then our R value is negative. So how does that work? So first time seeing this here. So positive degree, negative R value. And so we say this, it will say if we're at 150, we want to be here. We want to be along this line right here. That would be about negative 150. So then the question really is, if this is 150, looks like I have a 30 degree, don't I have a 30 degree angle between negative 150 and negative 180? 30 degree angle right here. That's where my dot would be. So if that's 30 degrees, we call it a reference angle. think we've seen it before. That means this has to be a reference angle. All right, what do we got here? Notice this is the exact, almost like you think about it, it's a 180-degree difference. So instead of going towards the angle measurement, what you do is you go away from the angle measurement. So this would be -2 units away from the 30-degree angle. So this would be, instead of going this way, I'm going to use this angle here, and that'd be 2 units going this way. And so what I say is I'm going to go the exact opposite way, away from that. There it is. So it's -2, 30 degrees. All right, C, what do we have here? I want a positive R value, and I want a positive angle. So looking back at A, think about it, instead of going clockwise, I want to go counterclockwise. I'm going to go like, okay, what is this right here? What's that going to be? It seems like it's going to be 180 plus 30 more, right? Because that's the reference angle. So 180 plus 30 more, I think that's 210. 210 would be it. So C value, here it is. I want to go the positive way. It's going to be a full angle plus 30 more because of that reference angle from the previous. So that angle is 210. There it is. Positive R value, positive degree value. All right, and the funny one of them all. What we want to do is we want to construct a negative R value and a negative degree value. Again, these are all the exact same point. All right, so we want to eventually end up right here. Since we want a negative degree value, we want to end up here going the other way. So that's the 30 degrees, right? That's the one that we did earlier. So I want to go the other way. So clockwise, I want to go this way. That would give me a negative angle. And since I'm 30 away from a full revolution, thinking that's probably going to be a negative 330 degrees. Since I end up here, and then since I want to go the other way, I'm going to put a -2 there. Okay, so all these four, A, B, C, D, all those are really the same exact point, just written differently and using negatives and positives. I know that does not happen in the X and Y grid, but it happens with polar coordinates. All right, so how does polar coordinates relate to X and Y coordinates? So here it is if you think about it. So we have an X and Y grid like this. R value comes here. Theta is, R value is here. Theta comes across here. So notice you actually could have polar coordinates, or you can actually have rectangular coordinates for the same exact dot right here. So that's what we want to do now. We want to be able to convert from one form to the other. We want to be able to convert from polar coordinates to rectangular coordinates, and then from rectangular coordinates to polar coordinates. Let's begin. All right, and we begin with trigonometry. If you think about this here, isn't this right here a triangle right there? Isn't this R value kind of like that hypotenuse, right? If I can form a right triangle here. I'm thinking remember how this used to be the X used to be cosine of, remember in when we first started trigonometry, remember how the X value used to be the cosine of theta, right? And Y used to be sine of theta. We're going to use that relationship. Now that was for the unit circle. So now the question is, what happens if you have this R value next to it? All right, and there is what we want to see here. So remember how sine of theta used to be the Y value over R? Cosine theta is X over R. So let's do this here. R stays the same. The R value, this little length area right here, is going to be the R squared, being X squared plus Y squared. But if we multiply both sides by R over here, let us sine theta. Take this guy, multiply by R over here, take this side, multiply by R over here, and we get this situation happening, that X is technically R multiplied by cosine of theta. The Y value is technically just R multiplied by sine of theta. All right, so let's use this little relationship real quick. All right, convert polar coordinates to each of the rectangular coordinates. So -360 degrees. Let's see if we can graph that first in polar coordinate wise. So let's see, that's going to be 60 degrees. So it's going to come up, not quite 90, but 60. All right. And then the other thing is we have a negative r value in our hand, so we're not going towards the angle, we're going away from the angle at exactly an opposite direction. So there's my 60, and I'm going to go this way, the exact opposite way. There's where my dot is. All right, so how can this little 60 degree help us? 60 degree is still the reference angle, so if that's 60, that means this guy also has to be 60. All right, so what do? Well, you can take the negative angle as well, but we normally like to have the r value being positive. So you want to secure that r value to be a positive value. And let's go for it here. All we got to do, plug in the formula. The x value is r cosine of the degree value. And cosine of 240 degrees, you can look that up along the unit circle if you like, and then go from there. But you should end up with a negative 1/2, and multiplying that through, how about a negative 3/2? The y value is going to be the r value, which is 3. Now it's going to be sine of 240. All right, if you know your trig values pretty well, you're going to say sine of 240 is a negative root 3 over 2. And then the 2 and the 3 don't cancel, so let's multiply that together. And how about a negative 3 root 3 over 2? There it is. There's the rectangular coordinate for that polar, that point in polar coordinates. There it is. We've converted from polar coordinates to rectangular coordinates. All right, b. Let's try b now. 2 comma negative pi over 4. So what's the changes here? First of all, the r value is positive already. That's already good for us. The angle measurement is in radians, so that's one little funny thing there is, and it's negative as well. So let's see what happens here. All right, thinking about this, what this would be in fourth quadrant, and it's a negative pi over 4, and we're going to go out 2 units. So now the question is, what's the positive value of it? Positive value is 7 pi over 4. All right, you can, some students do like to do it this way right here. They like to figure out the positive value. You can also work with the negative angle as well. So as long as the r value is positive, you're good to go. So even though you could put in 7 pi over 4, you can also use negative pi over 4 as well, and that would work just fine. Okay, again, some students just like to make sure they get the positive value, but any one of them would work just fine. All right, thinking back to the unit circle and finding 7 pi over 4, if you're going to use the unit circle, you're going to find out this guy is a root 2 over 2, and then eventually the 2 is going to cancel, giving us just root 2, or square root of 2. For the y value, it's going to be 2 sine of negative pi over 4. Looking at the unit circle, if you have it in front of you, or just considering this is a 45-degree angle, you could do it that way. But sine of negative pi over 4 is going to be a negative root 2 over 2, and eventually get a negative root 2 or square root of 2. All right, final answer. There it is, the x coordinate and the y coordinate, and we are good to go. So that is converting from polar to rectangular coordinates. Now let's go the other way around. This one's a little bit more complicated here. So we've got to figure out the quadrant in which this given point lies into. We'll figure out the r value using the x and y coordinates, squaring them, adding them, and taking the square root of them. And then here's a little problem. The angle measurement, we're going to use tangent theta over y over x. Now the only issue that we have is when we do this, we have to figure out which quadrant it lies in so that we can adjust our angle measurement. And I think we've done that before. All right, so let's go for it. So find the polar coordinates of -1, -1. That's where we're at. And yes, you have to state r usually is positive. Remember, because there's 4 different ways to write it. You want r to be positive. We want the angle measurement to be in radian measurements, and it's just positive, and it's the first revolution of it. That's the normal kind anyways here for us. So let's go for it here. So first things first, let's graph this. -1, -1. Everybody agree it's somewhere over here. We'll go -1 to the left 1, down 1. It's about right there. Okay, -1, -1 is the rectangular coordinate of this. So now let's go for it. Let's figure out the polar coordinate of this guy. So first things first, let's figure out the r value. Taking the x-coordinate, squaring it. Taking the y-coordinate, squaring it. Adding them up to become a 2. And how about a square root of 2 for that value itself? Cool. R value is taken care of. Now let's talk about tangent. So I've done this before already when we used to do inverse tangent functions here. So theta is equal to tangent inverse of the y-coordinate over the x-coordinate. Now notice what happens here. When you take a -1 over -1, the negative signs go away because the negative signs get canceled. So when you get the answer to this, you're going to get yourself pi over 4. You're going to get an answer that's actually in quadrant 1. That's what we've got to think about. Hey, we got an answer of quadrant 1. That's pi over 4. But what I'm really in quadrant 3. So what do we do to get to quadrant 3? Well, we just have to add a pi, right? A whole half unit or half a rotation. So we're going to take pi over 4, add 180 degrees if this was a degree measurement, or just pi because we are in radian measurement here. So how about this? The angle that we just got from tangent plus half of a revolution. All right, yes, we do have to get common denominators together. So how about pi changes into 4 pi over 4, and voila, there is my angle measurement in radian measurement. But that's the answer. So let's put in r value as √2, and theta value is 5 pi over 4. There it is, to finish it off. All right, now let's look at not just converting coordinates. So what we just did so far is actually convert certain points or coordinates on the Cartesian coordinate or the polar coordinates. Now what we want to do is we want to change to now equations. So there's some polar equations right here. Notice it's a relationship between r and theta. And instead of the x, you know how we have x and y, we plug in the x to get the y value? For r comma theta, theta is what we normally plug in, and then we get the r value out. So it kind of works a little different as well. All right, so some example of polar equations. Polar equations is the relationship between r and theta. All right, so r is equal to sine of theta. That is a polar equation. R is equal to 1 plus cosine theta. That's a polar equation. In fact, the weird one here, r is equal to theta, just like x is equal to y. That is also a polar equation. Right? So as we get into it, we'll see some fun looking stuff there. All right, so how do we do this? How do we convert between rectangular and polar coordinates? Again, we're just going to replace x with r cosine theta. Anytime we see y, we're going to replace it with r sine theta. That's it. So let's do some examples here. Or an example. How about that? All right, let's go for it here. So looking at this here, and then we're going to go back to our trigonometric rules here. And we're going to take some stuff that we know about trigonometry as well. All right, but first, let's replace any x's with r cosine theta, any y values with r sine theta. So I see over here, first one's first, there it is. R cosine theta being squared replaces x squared, and r sine theta squared replaces y squared. Oh, went a little bit too fast here. There should be like this little 2 right over here. Right there. Now that's my mistake here. Kind of went a little bit too fast there. Okay. All right, let's see what we got here. The y value got replaced with r sine theta. That's cool. Then plus 3, and that's going to equal 0. So we're good there. So now how do we square this stuff? Well, because there's a multiplication here, the r gets squared and cosine gets squared. So there's that. Now this one's going to be r squared sine squared. And this one's just going to be a multiplication into here, since everything is multiplication here as well, so it just becomes 2r sine theta. There it is. And the rest of the problem comes in. Okay. And then we have this little interesting concept in trigonometry, isn't it? Let's factor out an r squared over here. That would leave us cosine squared theta plus sine squared theta. And do you remember a rule somewhere that we studied? Maybe chapter 5, maybe chapter 6, that gives us some kind of identity. Yes, it's called the Pythagorean Theorem identity, right? Sine squared theta plus cosine squared theta is equal to 1, or cosine squared theta plus sine squared theta in this case equals 1. So that all just becomes 1. 1 times r squared theta just gives us r squared. All right, and the rest of it is here. So now what do we need to do? We need to solve this. In fact, actually we can stop there. That is it. There's, at least for now, there's the relationship that we have here. So we've converted an equation in rectangular coordinates to an equation in polar coordinates. All right, now going the other way. How do you convert from polar to rectangular? This is where the fun begins. All right, so what we're going to do, whenever you see r cosine theta, you're going to convert it to an x value, back to a y value, and then to get the theta measurement, sometimes we'll need that, we'll have to use y over x. So let's go for it here. All right, this is the more complicated one, so we're going to do a few more examples of it as well. So let's go for it here. So r equals -5. What shall we do here? Well, we can't convert r. We can convert r squared. So here's what we're going to do. We're going to square this side. We're going to square this side. In this case, r squared on one side and -5 squared on the other makes r squared is equal to 25. That's cool. Now, do we have a relationship between r squared and rectangular coordinates? Absolutely, yes we do. It is x squared plus y squared. And there it is. And if you guys remember all the way from, I think, the end of chapter 1, isn't this actually a circle at the origin with a radius of 5 units? So if you write r equals -5 or r equals +5, in fact the negative doesn't even matter at this point, you're going to get yourself a circle, 2, 3, 4, 5, of radius 5. That's what r equals -5 means right there. So that means the same thing as this. So if you're to graph r is equal to -5, you'd pretty much graph a circle, radius 5. If it says r is equal to -5, you'd in a sense go backwards this way, but then you still form the same circle. All right, so that's the weird one with r. R by itself, nothing else, forms circles. How about theta by itself? How do we change that into rectangular coordinates, and what does that mean? All right, let me finish this up. It means a circle. That's what we're going to label those. All right, for B, I see theta. I don't see any r value whatsoever. It's almost like the r value is missing completely. How do we figure this out? What we do is we put tangent on both sides. So now it becomes tangent theta and tangent of -π/3. That's how we convert it. And now the question is, what is tangent of -π/3? Okay, look at your unit circle if you need to here. Go for it here, and you find out that you get something over here on the one side, but tangent theta itself from the previous slide just becomes y over x, right? Because that's the rectangular equivalent of this one. Tangent of -π/3, that just becomes -√3. All right, what do we do here? Let's multiply both sides by x, because in rectangular coordinates we want things solved for y. And once it is, we're done. What does this look like? Doesn't that look like, and tell me if I'm wrong here, doesn't that look like a straight line? In fact, if you want to write it like this, I think you'll remember what this means. This is just y equals mx plus b. That's what it means. There's my y, equal sign. My slope is negative root 3. That's my slope. My b value is 0. And there it is. So in rectangular coordinates, in polar coordinates, if you see theta by itself is equal to some kind of constant, theta equals a constant, really what that means is you got yourself a straight line through the origin, which could be transferred into y equals mx plus b form. All right, let's do the other ones here, C and D. Now we do have a relationship between r, but not cosine or sine. It's actually related to secant theta. Okay, let's see what that means, and then we'll do a normal one right here. D would be actually the normal one, where you have a relationship between r and a trigonometric form of cosine or sine of theta. All right, so C, still the weird one. Let's try it. Secant theta. In fact, let me rewrite it on the next slide because I'm going to run out of space here. So CR is equal to secant of theta. What do we do here? Well, what we do is we just take the reciprocal of secant, because I want everything in terms of sines and cosines. If I do that, that becomes this right here. That becomes 1 over cosine theta. And if I were to multiply both sides by cosine theta, I think I would get this right here. R cosine theta equals 1. And I think I have a relationship. R cosine theta is technically the x coordinate. So how about x equals 1? There it is. So R equals secant theta in polar coordinates translates to x equals 1 in rectangular coordinates. I know how to graph this one. Graphed it a long time. I think that's a vertical line at 1. So that's what that means. Okay, so let's go back to what we know here. So if I have R value is related to a reciprocal of sine and cosine, it's going to either be horizontal lines or vertical lines, just depending on which one it is. All right, D, the normal one. All right, let's see what this one here. So initially it's R is equal to 2 sine theta. Okay, how do we deal with this? And what is it? What does it come up to be eventually or later on? All right, what we do here is instead of squaring both sides, what we're going to do is we're just going to multiply both sides. All right, don't forget it, y is equal to r sine theta. So I want an r inside here. Instead of it being 2 sine theta, I want a r in here. The only way I can do that is to multiply this side by r and this side by r. So let's do that. So multiply left side by r, right side by r. That gives me r squared on one side, but a 2r sine theta on the other. All right, once that happens, I can substitute what I need. R squared, remember, is y squared plus x squared plus y squared, sorry. This one is just going to give me 2y. Well, got ourselves a little problem. If that y squared was missing, that would have been cool. We just divide both sides by 2, we solve for y. But here I see a y squared, I also see a y over here too. Here's what I'm going to do. I'm going to move this over, set equal to 0, and let's see what happens here. So let's move that 2 over to make a minus 2y on one side. And then, if you guys remember something called completing the square. Completing the square means I'm going to make a perfect square over here, and I'm going to try to make a perfect square over here. I'm going to leave a little bit of space. I'm thinking to myself, you know what? Y squared minus 2y plus what? What here would give me a perfect square trinomial here, so I can make it into a being binomial squared. And so I know this has been a long time ago, but what we do is we take this middle term, negative 2. What is negative 2 divided by 2? And that's going to be a negative 1. And if we square negative 1 times negative 1 is positive, and that's exactly what we'd add in. We added it here, but we also better add it over here as well. So x squared is good by itself. That's already a perfect square. this guy's going to be y squared minus 2y plus 1. Is that a perfect square of something? Yeah, right here. Isn't that y minus 1 and another y minus 1? So this is y squared. This would be a y minus 1 squared is equal to 1. Okay. There it is. What does that mean? That means this is a circle. And if we draw it out, remember this is a circle. I think this is the end of chapter 1 with center at 0, 1. That's the center. Center is at 0 because there's nothing added or subtracted to x to make that a perfect square. For the y, the 1 would make this a 0. So 0, 1, there's my dot, and it has a radius of 1. So it goes out 1 unit in every direction here. So it goes that way right there. There's my circle radius 1. I think we did this at the end of chapter 1. I think we had circles that we were looking at. All right, so there it is. What happens? It forms a circle. All right. Now we move on to, let's start graphing these polar coordinates. And before we do that, we're going to do one more little thing here just to cover, to make sure it's all complete here, is just the whole concept of symmetry. How do we do symmetry in regards to polar coordinates? Well, our positive theta, if you were to go back across the x-axis if you wanted to, here's the only thing is to test for x-axis symmetry. What we do is we put a negative theta in for what we have here. So negative theta. If you put a negative theta and you come up with the exact same equation that you had before, you got yourself symmetry with respect to the polar axis. Alright, the other one is theta is equal to pi over 2. Now remember, this is technically would be the y-axis, right? But because we're in polar coordinates, it's symmetric about theta being pi over 2. So in this case, what do we do? How can we tell that this is the same thing as this, or would graph the same? Well, we can do it one of two ways here. We can either look at the theta measurement. So notice the relationship between here and here. This would be theta minus, pi minus theta if it was here. Or you can do is you can bring it down this way. That would be negative theta, because this dot would go down here. And then you do negative r. And that would see if you had the same exact point, and they're related by symmetry. All right, and how about symmetry about the origin, or symmetry about the pole? In this case, we already pretty much have seen this here. It's going to be a half a revolution. So if you were to add pi to the angle measurement, the question is, would you still end up in the same spot? Or you can do it the other way. You could just, if the r value is negative, if the r value turned negative, would you end up in the same? Would you get the same thing initially? And yes, you would. All right, and I've been talking about the unit circle here a few times here. Unit circle, unit circle. This is the unit circle that we talk about here. This one actually has all the degree values, radian measurement, and all the x and y coordinates associated with all the points that we can get exact values for. Okay, where's this at in your textbook? It is on page 509. So 509 has this little relationship there. All right. So if you want to refer back to it, page 509, if you sort of want to have it in front of you, if you have your textbook. If you want to print this out, that's fine too. I know it's going to be on the notes as well, so if you need that as well, so it's there. All right, so let's start. Let's start graphing basically polar coordinates. So sketch the polar equation of r is equal to 2 theta. What in the world is this? Why is that little 2 there? The relationship between r and theta is right here. And in the example, for example number 7, it says what happens if theta is positive angle. Here we're going to go with negative angles of theta. So let's see how this pans out. So because we want negative angles, we're going to make ourselves a little table, because we can always make a table, right? So we could plug in a 0 into here. And if we plug in 0, notice the relationship is just double, right? You get whatever your angle is, you double it. So 0 times 2 is still 0. So now we're going to plant our coordinates here. So remember, coordinates are r theta, not theta r. Even though we plug in for theta, we get the r value. The way we write the coordinates is r comma theta. Okay, let's set this up. This is going to take a little bit of a long while here. So sit back and let's get going with it here. So 0, 0 would be the first coordinate we're going to graph. Alright, so here's a few things I've got to think about. Sometimes what the book does, it goes by pi over 2. If you want to get a little bit more precise graph, you can go by pi over 6. That's fine. Some books, they make you do every single coordinate from that little previous unit circle that we just did. So you find out pi over 6. You find out pi over 4, you find out pi over 3, you find out pi over 2, and you sort of go through each mix. It doesn't matter which way you go, the more detailed the better. That's what usually is stated. So if you can go by a little bit, crunch more numbers, of course you're going to get a little better graph. Okay, so for this particular one, we're going to go by multiples of pi over 2, because that actually would be enough for this graph. Okay, so let's go for it here. So if you plug in negative pi over 2, plug it into that, the 2's are going to cancel, because you're doubling something, you're going to get negative pi. Alright, and the coordinate that we get from here is, let's see, theta is negative pi over 2, and the r value is pi. Keep putting in the next one here. How about if we put in negative pi? So that means the answer would be negative 2 pi, because we're just multiplying through by 2. And here we go, putting in a theta of negative pi gives us an r value of negative 2 pi, closing that off. And negative 3 pi over 2. Multiplying by 2 would just give us negative 3 pi, because again, it's just this relationship right here. It's the relationship between r and theta. You're just doubling whatever theta is to give you the r value. In this case, there it is, plug the input value, the output value, and close it off. Input value is negative 2 pi, times 2 makes negative 4 pi, and there it is, input value, output value. Alright, so with that, let's start graphing. Let's start graphing this here. So setting it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm doing a little grid here, 10 by 10 grid. Oh, went a little too fast here. So with 0, 0, that's going to be, again, at the origin. Doesn't really matter what degree it is, because the r value is 0, so it does not go away from the origin. The next one. Let's see, negative pi over 2, so this is going to be a negative angle, and then we're going the opposite direction, because this guy we're going to go about 3.14, so a little bit above 3. So using our polar axis right here, we're going to go down or clockwise pi over 2. This is negative pi over 2, but then because it's a negative pi value, we're going to go 1, 2, 3, and a little tiny bit above there. Alright, 2 times pi is 3.14 times 2, which is about 6, a little bit over 6. So now, again, negative pi over 2, negative pi makes it over here. But then we're going to go this way, 1, 2, 3, 4, 5, 6, and just a little bit more. Alright, so again, and now this is going to be negative 3 pi over 2, so now we're going to swing this way all the way to here. Here's our angle. Our angle measurement is right here. This is negative 3 pi over 2, except we're going negative 3, so 3 times 3 is 9, 3.14 is a little bit over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and just a little bit beyond that. Alright, for this one, this one's even going to go off the chart here. So this is 3 times 4 is 12, so we're going to go negative 12. So this is negative pi over 2 is the angle measurement. So we're going to go and all the way full around the unit circle like this, and going back one full revolution. So we're here along the polar axes, but we're going to go this way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 3 times 4 is a 12, so it'll be negative 11. 12 and a little bit more than that, so about right there. And I don't think that sort of gives us a picture of what it looks like either. So if you want to put in some more points, that's totally okay too. I'm going to put in a pi over 4, because that's like 45 degrees. And again, negative pi over 4 times 2 makes a negative pi over 2. Here's what I got here. Input value, output value. Close it off. So if we think about this here, this would be about 1.7, right? 3.12 divided by 2. 3.14, sorry, 3.14 divided by 2. So we're going to go negative pi over 4, and then we're going to flip it the other way. So there it is. Yeah, somewhere around 1.6, 1.7, because 1.7 plus 1.7 would be 3.14. No, it won't be. No, a little bit over 1, right? 3.14 divided by 2. Yeah, that would be about right. Okay. And then another one here. Let's go with 3 pi over 4. Plug that in. You get a pi over 2, 3 pi over 2. And there it is. Input, output. Closing it off. So that means if we go negative 3 pi over 4 would land us in quadrant 3. But we're going to go the opposite way. So 3.14 times 3 would make 9. So about going up 4.5 units. So kind of just sketch about 1, 2, 3, 4.5, somewhere in there. Okay, now can we connect the dots? So we connect the dots that are sort of close to each other, and we kind of see what's happening here. And notice if we were to go from here to here, right? Notice what's happening. It's almost like it's called a little spiral, isn't it? Spiraling out, there it is. Alright, and then as I looked at the answer right before you start the homework, there's always answers for each of these practice problems. And I noticed when I looked at the answer actually is wrong. This is the correct answer here because we're dealing with negative angle measurements. The person that was doing the problem probably was doing it too late at night and didn't realize that he was going the positive way instead of the negative way, but this should be the answer to it. All right, so what is this? This is a spiral. That's what it is. All right. Some more spirals you may consider here, right here. This is the one that we did. So it kind of goes out in a different shape. We're either spinning clockwise or counterclockwise. If you wanted to go out a little faster with magnitude and so on, and notice this one starts at the origin. This one does not start at the origin. It starts off a little off to the side here. In this case, it's going to be a to the k times theta, and theta is actually inside the exponent here. So a few little things there. So there's two types of spirals right there. Let's go with practice problem number 8. Now let's deal with this here. Let's graph r is equal to 2 times 1 plus sine theta. All right, this one's going to be a long problem here. Gear up for it here. And then it looks like we have just one more problem after this. So this is the second to last problem, but it's a long one. All right, if we don't know what graphs look like, we can always make ourselves a little table. So I'm going to make a theta table, a r theta. So R table and then the number themselves here. Okay, so let's go for it. I'm going to add a few more here, like that. I think that's what I need in order to get through at least up to a revolution here. Okay, this should tell you your domain as well. This time they don't show it to you. It should say from 0 to 2 pi. If it's a 0 degrees, 360 degrees, that means you're in degree measurement. This time you're just in, you naturally assume that you're in radian measurement. We use that more often. If it's a degree measurement, most likely it will tell you that this is in degree measurement. All right. So let's go for it here. I got myself 0. And this time I'm going to choose all the values we know. We know the exact value of pi over 6, pi over 4, pi over 3. Think of your multiples of your 30 degrees and multiples of your 45 degree angles here. So pi over 2, 3 pi over 2, and again, you can go around the unit circle if you like. That unit circle on page 509 in your textbook. You can go around that, and eventually you're going to get to pi here. So I got a half revolution, and let's see where we're at. Okay, what you have to do is you have to do a lot of calculations to get to where we need to be here. Okay, so you're just going to plug in values, get the value, stick it in for r. So in this case, it's going to be sine of 0. Sine of 0 is 0, and 1 plus 0 is 1, so therefore 2 times 1 is 2. All right, going with the next one here. It's going to be sine of pi over 6, and again, using your chart is probably the easiest way to do it. Sine of pi over 6, that will be 1/2, and 1/2 plus 1 is 3/2, and then you multiply that times 2 and get yourself 3. So let me fill this in here. So r value of 2 from a 0 value for theta, r value of 3 from a pi over 6 value of theta. Okay. Keep on going here. Let's see. Now the next one is pi over 4. So pi over 4. And that's going to be square root of 2 over 2. Oh, hold on. Let me finish. Yeah, sorry. I forgot the in that parenthesis there on that previous coordinate here. So there it is. So this is going to be sine of pi over 4 is really 2 root 2. And this one you may want to just sort of simplify this way here. Let's just distribute the 2. That's probably the easiest way to simplify. 2 times 1 is 2. 2 times this, it cancels off the 2, so you're just left with square root of 2. So I'd write 2 plus root 2. Now, do you need to convert that into an approximate decimal? Yeah. The way we normally convert it, we think of square root of 2 as a 1.4, because 1.4 times 1.4 gets close to 2. So 1.4 is sort of the approximation for root 2. All right, so output for the input. There it is. Next one is pi over 3. So sine of pi over 3, that's going to be 60 degrees. Using unit circle, you find out that is a root 3 over 2. And again, distribute the 2 inside there. How about now a 2 plus root 3? So punch that in. What do we use here? All right, and the approximation is, if you take the square root of 3, you'll find out it's like 1.73. So 1.7 is what we normally use as an approximation, 1.7. If you need the decimal approximation here, so output and input, there it is. Okay, then we got to fill in some more here. So go for it. Keep on going. I'm going to just let you to fill that in here, give you a little bit of time to fill in. This should be very similar to what we've done before as well. So pi over 2, sine of pi over 2, and that's going to be 1. 1 plus 1 is 2, and 2 times 2 is 4. So if you were to do that, again, I'm not going to do it here, but you should see this done. And so I think you guys are capable enough to punch in pi over 2 and simplify it. All right, and as you do the other ones here, again, you please try it yourself here. I'm not going to write them all down here, but try it yourself, and you find out that you have this little pattern. It goes, the next output is going to be 2 plus root 3. The next output after that would be a 2 plus root 2, and yes, it is a pattern, of course, because it's a trigonometric form, right? So trigonometric functions are repeatable, right? They go back and forth, they go up and down. So as you punch in the pi into this, sine of pi is 0, 0 plus 1 is 1, and 1 times 2 is 2. All right, so let's see what this looks like. Let's see. Okay, so if you guys can, start a little graph for yourself already. Can you start a graph for yourself? See what you get. I'm going to start it as well here, so if hopefully your graph matches up with my graph. So let's see where we're at. All right, and the way I like to start graphing is to figure out what was my highest R value. From the previous slide, look at your highest R value. I didn't think it was 4, so what we're going to do is we're going to graph out only 4 units because that's the farthest we need to go out in this particular graph here. All right, another thing that I like to do is take a look at all my almost like my x and y coordinates. I like to take a look at what happens here along the polar coordinate, along theta is equal to pi over 2, and along this one here. All right, so first point is 2, 0, so 0 degrees. I go 2 units out. So what happens now at pi over 2? Where are we at pi over 2? Look at your previous slide here, 4, pi over 2. So I'm here, and again, that kind of gives me an idea of what I'm going to be doing here. And then also at pi, what happens at pi? Pi, I'm out 2 units. So there it is. Now I'm going to fill in the rest of them and see what they look like. So going back to pi over 6, my 30-degree angle here, it's 3, pi over 6 from the previous slide. So I'm going to go out kind of like this right here. That seems to be like a 30-degree unit right here. And so I go out 1, 2, 3 is about right there somewhere. That's about 30 degrees, maybe a little more than 30 degrees, but that just kind of fills it in. 45 degrees or pi over 4. I'm going to go out 2 plus root 2. So root 2 is 1.4 plus 2 is 3.4. So 3.4 units. I'm going to go out this way here. 45-degree angle. I'm going to go out just a little further than that. Yep, that's about right there. Pi over 3 is 2 plus square root 3. Square root 3 approximation is 1.7. So we're going to go about 3.7 units. So 60 degrees about right there like this. And we're going to go at 3.7, and notice especially this kind of gives it away, especially what kind of shape I'm going to have here. Okay, and then remember how on the previous slide for the r values went from 2 to 3 to 2 plus root 2, 2 plus root 3, it went up to 4, then start coming back down. So from this side, you know that's going to be symmetric. It's going to come back down like this. So we're going to go 2 pi over 3, about 3.7. 3 pi over 4 comes out about 3.4. There's my 3 value, and then again I'm back down to here. So that's what I got right here. This is sort of my shape. So I'm thinking to myself, notice since we have sine on our hands, sine is positive in quadrants 1 and 2, right? Sine becomes negative in quadrants 3 and 4. So it won't be sort of symmetric this way. It's symmetric along theta is equal to pi over 2 because of sine. So I wonder what's going to happen underneath here, especially when sine goes negative. All right. So let's go for it. Here's what we're going to do. We're going to take the second half of the rotation here. And so again, finishing, putting all these in here, I have to sort of count them. So I'm going to go, okay, if I go past this, past 180 degrees or past pi, the values that I know from a unit circle are 7 pi over 6, 5 pi over 4, 4 pi over 3. That gets me down here. Now I'm looking at this value here. That's 3 pi over 2. Moving off of that gets me a 5 pi over 3, 7 pi over 4. And eventually, right before I hit a full revolution, 11 pi over 6. And if you want to, you can fill in the 2 pi as well. That'd be fine. Okay, so here's what we'll do. We're going to calculate these guys, and then we're going to make a full graph of them here. All right, on the next slide, let's calculate all these guys right here. And again, if you'll follow along, if you want to slow down, because I'm going to do it kind of quickly here just to make sure I get it done. But if you want to slow the video, that's fine too. So let's go. I think we have enough room here on this one just to give us the first one, 7 pi over 6. Let's go with it. So 2 times 1 plus sine of 7 pi over 6. And then again, using your unit circle, the sine of 7 pi over 6, the y value or the y coordinate would be, looks like it's going to be a negative 1/2 this time. Okay, so 1 subtract a half is a half, and a half times 2 is a 1. So this time, instead of adding, we're subtracting from the 2. Okay. Let's keep on going with the rest of them here. All right, let's put this down. 1 and 7 pi over 6. All right, the next one on the list here is 5 pi over 4. And again, if you can do this in your head, you're doing great. 5 pi over 4 would give us a value of sine at negative root 2 over 2. Multiplying the 2 into it would give us a 2 minus root 2. All right, the next one is 4 pi over 3. So sine of 4 pi over 3. That is going to be a negative, I know that, root 3 over 2 this time. Multiplying the 2 in gives us 2 minus root 3. All right, next one on the list. How about a 3 pi over 2? That's going to be sort of going down, and that's going to be a negative 1 for sure. So it's going to be 1 minus 1. Ooh, this one gives me a 0. I'm not going anywhere. Away from the origin. Okay, let's get the other ones done here. Let's see. After that one, what we have is we have a 5 pi over 3. And when we do that, again, it's the symmetry that happens again. That's going to give you a negative root 3 over 2. Distributing that out gives you a 2 minus root 3. Punching in the next one here, which is 7 pi over 4, or 315 degrees if you like. And that's going to give me a negative root 2 over 2. Distributing the 2, it gives you 2 minus root 2. And the last one as far as rotation goes, and we'll do one more here beyond that. So 11 pi over 6, almost at 360 degrees, or 2 pi. And that gets you a negative 1/2. From 1 gets you a 1/2, and multiplied by 2 gets you a 1. And then just to finish it off, let's put in 2 pi. So sine of 2 pi, that should be the same thing as our first one that we did. And so sine of 2 pi is 1. So 1 plus, I'm sorry, 0. Sorry, 0. 0 plus 1 is 1, and 1 times 2 is 2. Okay, can we fill in that chart now of the stuff that we know, and then can we finish filling out our graph? Let's go for it. So from the previous slide here, I'm just going to fill in the rest that I know. There it is. 2 minus root 3 was for 4 pi over 3. When I plugged in 3 pi over 2, gave me a 0. When I plugged in a 5 pi over 3 from the previous slide, gave me a 2 minus root 3. When I plugged in 7 pi over 4, that gave me a 2 minus root 2. And then when I plugged in a negative pi over 6, that gave me just a 1 value. And then to finish it off, 2 pi. Plugging in 2 pi gives me a R value of 2. All right, based upon that, see if you can go ahead of me here. Can you? Can you go ahead of me and finish these off? At least try to graph them according to what we've been doing here. Okay, let's go for it here. So at 7 pi over 6, which means going beyond the 180 degree, or pi, so it's almost like this little angle right here, I'm going to go at 1. So whoa, that's probably going to be right here. It's a little under 1, but that's fine, about right there. Okay, square root of 2 is 1.4, but if you go 1.4 subtracted from 2, that gets you actually 0.6. So that 45 degree angle gets you a 0.6, maybe even scoot it in just a little closer, that's fine. 1.7, so 1.7 subtracted from 2 gets you a 0.3, that's about right there, maybe even closer to the origin. And then at the 3 pi over 2 angle, that gives you 0, so you're right there. And then on this side, let's see, 1.7, that's going to be 0.3. And this angle here is going to be 0.3 away. Here you're going to be 0.6 away. Here you're going to be the next angle, which is 11 pi over 6. You're going to be at 1. And then eventually notice what you're going to end up. You're going to end up with the same spot. So as you connect these coordinates together, you have something that looks like this. All right, what is this called? This is called a limicon. Limicon. All right, one thing I do want to cover with you is you can actually graph this on your calculator as well. So if you get pretty good at this, you can check, make sure you graph it the same way here. So let me go through the calculator way of graphing it. This is part of the textbook as well. Let's go for it. Let's see what we get here. So first things first, if you have a TI-83 calculator, any of the TI calculators, that's the one I'm going to show you. That's the one I have a sort of virtual of it. And what we do, first things first, before you do anything else, is you're going to go and get this little mode button right here. You're going to click on mode, and it's going to give you this menu right here. So on the previous one, these two rows are very important. Radian measurement versus degree measurement. And make sure this is highlighted. Then when you get to here, I'm pretty sure function is going to be highlighted for you. So what you want to do is you want to switch over here using arrow keys. And you want to click on pole for polar coordinates. Click enter. And so here's the highlights that you want to have on there. Okay. And then what you do, once that is set, you're going to go to this little button right here called the X, T, theta, or N. This is called the variable button. Now because we're in polar coordinates, kind of interesting, there's the R value and the theta. And that little theta right here, that's because you're in polar coordinates. So it gives you, like, if you're in functional coordinate, it's X. If you were in parametric equations, you would be T. Since you're in polar coordinates, you are theta. And since if you were in sequential form, then you would have had an N next to you. Anyways, punch this in here. For R1, punch in a 2 parentheses 1 plus sign. And of course, once you punch in sign, it's going to open up a parenthesis for you. Punch this little button right here for theta, and theta will pop up instead of X like you normally would. Close off the sign function and then close off the multiplication between the two. Alright, one more thing before we get to our graph is this whole concept of window. So click on this little window piece right here, and it's going to be a lot different than you're used to here. So when you click on it, you have 3 different variables to really make sure that you're going with here. So first of all is your theta. Since we're starting off at 0 and we're going 1 full revolution, you're going to go theta min is 0. Theta max is going to be 2 pi. So as you punch in 2 pi and use your pi key as well on your calculator. So once you punch in 2 pi, it's going to convert to 6.28 blah blah blah. And then this one is your step function. How often do you want it to calculate your steps? In this case, pi divided by 10. That's what we want to use here. Pi divided by 10, knowing it's 3.14, right? Divided by 10. So you do want to use the pi button though. So that would be pretty fast calculating right there. That going to gives us enough of a curve to sort of see it. Alright, according to the graph that we had an x min of -4, an x max of +4, and the scale was 1 for us. Alright, one more. As you scroll down by using the arrow keys, go down, 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 down. You got the last set of variables called the y variables. So again, y minimum is -4, y maximum is +4, and the y scale is 1. At this point, we are ready to graph. So what you want to do is you want to click this little graph button right here. We have everything set. We got our mode correctly. We've punched in our equation, and we've set our window. So click on graph, and you get something that looks like this. Now notice this is a lot fatter than the one that we had, right? That's because the screen is really not a rectangular screen. It's really a 2:3 ratio. So in order to see it sort of a little better, what you want to do is you want to go to zoom, and zoom. This is the zoom button right here. Click on zoom. And then you want to scroll down or just click number 5. You want to go to a square. Zoom square number 5. Either use the arrow keys or actually click the number 5. And then if you use the arrow keys, click enter on the bottom of the calculator, and immediately it's going to graph it again for you. But this time it's going to keep this little ratio correct. And so notice even the ratio, if you think about it, there's one click right here, that's 1, 2, 3, 4, 5, 6. So 6 x coordinates for every 1, 2, 3, 4, for every 4 y coordinates will make a square. And that's pretty much what we got there. Limicon. We got a limicon on our hands. Okay, so what are some other limicons that we have? All right, few things here. So a limicon is general. You can have an inner loop like this. Okay, so limicon, what it really has, it's almost like this little double looped inside here. If it reaches the one that we graphed, actually, if it stops at the origin and doesn't do a secondary loop inside, it's called a cardioid. And so Mr. H, where are these used at? Why do we need this? Oh, this gives you planetary motion. This gives you a lot of different motion, especially motion that's curved and motion that's oscillating. If it's going up and down, you can actually see the exact position of things. Comets, asteroids, all this stuff. Look, you think about what happens in space, that is it, and things that actually function on a oscillating or a double oscillating movement that's circular. That's what we use these for. Okay, so there's those. Some other limicons we have is something that looks like this, where it doesn't actually, we call it a dimpled limicon. It doesn't actually reach back to the origin. It doesn't have the secondary loop. It doesn't even get to the origin. So it's a dimpled limicon when it has a groove, a little tiny groove inside, and sometimes those just go flat down. Oh, boom, right here, not dimpled. It's kind of not exactly a circle. It has this little bit of a sort of flattened shape to the side of it. All right, let's do another one here, and this will be the last one. So what happens if the 2, instead of being outside of the sign, what happens if we scoot that 2 inside? Now we're dealing with the angle measurement itself. So this one says I plug in theta, whatever it is. I'm going to double my angle first, then I take the sine of it, and then that's what gives me r. So let's go for it. I'm going to make my values there. Come down a lot of them here. So I'll plug in a 0, and obviously 0 times 2 is 0. Sine of 0 is 0. Okay, you guys get to do this here. And you know what we're going to do? We're just going to go out to pi. That's what I want to do. I want to go out to pi. Because sometimes when you just do pi and you see what's happening, I ran out of room on the bottom here, so I'm going to do one more over here. Sometimes when you go half a revolution, you can kind of see what's going to happen the rest of the way. And that's exactly what you want to see. Like, oh, hold on. By that, I'm sure the rest of the way it's going to go like this. And then you can kind of see it all the way through. So not as long as we had practice problem number 8. Let's go for it. So everybody okay with that? So plug in a 0 into sine. 0 times 2 is still 0. Sine of 0 is 0. Boom. All right, plug in pi over 6. Now, when you plug in pi over 6, here's what's going to happen. It's going to double first, right? So technically what you do is you're going to just say, what's sine of pi over 3? Because you're going to double it as well. And look on your chart on page 509 in the textbook. You'll see it right away. You're going to say, oh, that's root 3 over 2. Perfect. So there's root 3 over 2. I'm going to do one more with you, and I want you guys to finish off the rest yourself. All right, finish off the rest yourself, and you do this here. So punch in pi over 4. So sine of 2 times pi over 4. When you do that, the 2 and the 4 reduce down to just the pi over 2, and sine of pi over 2 is 1. There it is. All right, all yours. Can you finish off the rest of it here? Give you maybe a couple of minutes here. Pause the lecture if you need to, and we'll go from there. All right, so let me set this up here. Hopefully you guys found the answers. I'm going to just list the answers for you here. So I'm beginning to end. There's that one. There's that one. All right, and the rest that you should have done yourself here. All right, if your answers match mine, you're doing great. If they don't, go back to your page 509 on the chart, see what went wrong. And for pi, punching in pi here, pi times 2 is 2 pi, and sine of 2 pi is a 0. Okay. With that, if you want to write it down real quick here, go for it in these things. All right, and let me start it as well here. So using these coordinates, we're going to graph the line here. So the highest value for r, let's check it out. Looks like it's going to be 1. The highest value for r is a 1. So our graph is going to be pretty zoomed in. Here it is. Here's 1 out. In fact, this one could have been out a little further here this way, but all right, let's go for it here. So based upon the previous slide, 0, 0 is the first point. It's at the origin. Pi over 6, or 90 degree or 30 degree angle. We're going to go out. Let's see, it's going to be root 3 over 2. So 1.7-ish divided by 2 would be 8.85, right? That's about 0.85. Pi over 4, the 40 degree angle, goes out 1. Now, it's not going to be 1 unit like this, like you normally charted on X and Y grid. You're not going to go out to here. You're going to go out about approximately this length, but this way. That's about a 1, maybe a little further, maybe just a little bit, but that's about fine right there. All right, at pi over 3, it's going to be root 3 over 2 again, which is about this one, and this one. I think maybe it's about right there. All right, at pi over 2, which is this way right here, we get a 0. So we're back at the origin again. All right, at 2 pi over 3, which would be right over here, it's actually a negative 3 pi over 2. So we're going to actually go backwards. So this angle measures out this way. We should have been going out this way, but we're going to go this way because of the negative value of it. And 3 pi over 4, again, 3 pi over 4, we should have went this way here. 3 pi over 4 should have been going out right here, 135 degrees. But because it's a negative 1, we're going to go the other way right there. All right, and 5 pi over 6. 5 pi over 6 would have been right here, 150 degrees. And since it's a negative 3 over 2, we're going to go that way. And then once we get to pi, again, back at the origin. So let's see if we can sort of graph this out, okay? We're going to go according to the dots, just exactly the same sequence that we graphed, and we're going to connect them. So from the origin, that was 0, 0, we're going to go out and sort of hit the first dot, get to our second dot, go to our third dot, go to our fourth dot, go to our fifth and sixth dot, and then how about 7th and 8th dot? And that's only half of a full revolution of 2 pi. So think to yourself, okay, if this keeps on going, which way is it going to go? And I'm thinking, you know what? That keeps on going. It's going to go like this. It's going to go to this dot, then this dot, then back down to this dot, back to origin. Then it's going to go up to here with a dot, out, furthest it's going to go out, comes back, and back down. So there it is. There is what we have here. All right. What is this one called? I'll show it to you later. This is called a rose curve. These are rose curves right here. Let's see how we can do this on a calculator, though. This will be the easier one. Let's go for it here. So go to y equals, punch in, instead of what we had before there, just punch in sine of 2 theta. Close off the parenthesis for that one. All right, then we have to adjust our window. Go back to your window right here, your window, and you're going to go to an x minimum. Let's keep everything above the same. X minimum is -1, x max is +1, and the scale is 1. Y minimum is -1, Y max is 1, and then this one, even though you can't see it, it's just 1. And at that point, click Enter for those guys. And then, of course, we can just go directly to a zoom squared, so don't need a graph and then go back. Click on Zoom right here, this little blue button. Go to number 5 for your square. Click Enter. And you're going to get something that looks like this. And you're going to say, Mr. H, why? Well, there's not enough dots to sort of give you a good representation. So notice for each thing in the quadrant, it's 1, 2, 3, 4, 5. You get 5 pretty much measurements. And the reason for it is because we're doubling everything here. So notice this is not the shape I want yet. I think there's too many. It should be a curve, and I have too many sort of sides and straight lines. So let's go back to our window, and the thing that we want to adjust is this little step right here. Now this one, remember how it was pi divided by 10? I'm going to do this. I'm going to say pi divided by 30. By the time it goes through one full revolution, I want it to take 30 calculations and connect 30 points together here. So this is pi divided by 30 right there. And then click back on graph when you get that done, and you get yourself exactly or very close to what we had before right there. There's your rose curve curving out, and that's kind of cool. Look at that. All right, so we did it by table, and we also did it by calculator. All right, what's the other stuff you will see on the homework here? This is in back of the textbook here towards the end of the section. Here's the stuff. There's the limicons that we looked at. The rose curves, there they are. And interestingly enough, it says if n is odd, if it's an odd multiplier, then the rose is going to have n petals right here. So this is A is just a length, how far it's going to go out. So A cosine 3 theta. And there is sine 5 theta. There's your 5 petals. If it has an even number of petals, then it's going to have always double that n value. So there's 4. That's the one that we drew right there. For cosine, there's 4. Now we're going to have 8 petals here then because of that. And it looks like a daisy. Not sure if it looks like a rose as much as a daisy here. All right, circles. We actually did graph something like that as well earlier. Lemniscates. That's the one that we haven't done yet. So if you see an r squared value there, you're going to have to do 2 graphs. You're going to have to use a square root of a squared sine 2 theta and a negative square root of a squared sine 2 theta. So again, that's going to be some work there. And then the spirals that we had before. All right, so that finished off the lecture for 7.6.